So this is problem 5.9 for standard 5.4. So it gives you a particles in an infinite square well, and the initial wave function is given as this. You notice the time is 0. And so it asks to find the wave function at a later time. So we want a t here instead. So first we have to normalize the function to find a. And so to do that, we find the integral over z over L psi x of 0 modulus squared. So we plug in our function and integrate it from 0 to L after we square it. And so that's going to give us modulus a squared times L over 840. So a equals the square root of 840 over L. So then we plug our a back up here. And so now it's normalized. So next we have to find the expansion coefficient, c of n. And so to do that, we're going to find the integral from negative infinity to infinity of, I forget what this symbol is called, of x times psi x of 0 dx. And so this is our energy eigenstates, and so it's defined as square root of 2 over L sine n pi x over L. And then we plug in our psi x of 0 from up here, or our normalized, make sure it's the normalized one, and then times d of x. And then you expand this out, and you get this nice ugly integral. So as easy as just to plug that into Mathematica and have that solve it. So what we're going to get is c of n equals 24 times square root of 105 over n pi cubed. And so there's our c of n. So psi x of t is the sum of n equals 1 to infinity of Cn, this thing again, x e to the negative I, our energy, and times t. And so we're going to plug in our c of n. Well, not yet. And then we already defined that that this is square root of 2 over L sine n pi x. And the energy E of n is n squared pi squared h bar squared over 2mL squared. So we're going to plug that in here, and then of course the t stays in also. And then so last step, I plugged in my c of n, which is up here. I plugged it in, and I moved some stuff to the outside, and you can move these out to the outside because there's no n value in them, and so that's the wave function at a later time. So the next part asks for the probabilities of energy measurements. So the probability of E of n is just the modulus Cn squared. So our C of n is this value. So we're just going to square it, and that's our probability, 60,480 over n pi to the 6th. There's supposed to be another parentheses bracket here, so it's the product n pi and then this product to the 6th power. And so the third part asks for the expectation value. And so the expectation value is the sum over n of our probabilities E of n times E of n. Or in this case, the sum of n of modulus Cn squared, so this value up here, times E of n. And as I said before, E of n is n squared pi squared or h bar squared over 2 ml squared. So you plug Cn in and En in, and you get this. And you can move all this out to the outside because there's no n value in it, and it's just the sum of n over n. So we're left with, the only thing left in the sum is 1 over n to the 4th, and that is equal to pi over 4 divided by 1440, and then so you're left with this. And I actually forgot to list a step in between, but this is going, all of this is going to reduce down, this is going to reduce down to 42 over pi squared E1, and that is because h bar squared over ml squared is equal to 2 over pi squared E1. And then so this is our expectation value, and that's the final answer.